to hear over me. Okay, so I want to talk about transformers to start with, and yeah, we're going to do a PowerPoint, but I'm going to switch back and forth a little bit to my own drawings, and then we'll continue from there. Okay, so a transformer, it's a non-mechanical device. Okay, so there's no moving parts in a transformer, or at least there shouldn't be. The transformer primary is the side that we apply voltage to. Okay, so we apply voltage to a transformer primary. The secondary side is where voltage comes out of. Okay, it's the output voltage supplied. Now, the transformer is one of these weird devices that's both a load and a source. The transformer primary and the secondary do not come together electronically. It all has to do with magnets. Okay, the transformer core, the center iron portion around which the primary and the secondary windings are wound, is what actually helps create and transmit this magnetic energy. Okay, so again, symbol for a transformer. We don't know what winding this is because it's not labeled. We don't know what winding that is. We know one of them is a primary and one is a secondary. The core is in the center. You can't draw a transformer symbol just with two coils of wire. You've got to put the two lines in there for a core, or no one knows what it is. Okay, so transformer, two windings. One is the primary, one is the secondary. The input AC, in other words, the power we're supplying, creates a magnetic field. The magnetic field creates a voltage on the secondary winding because, again, whenever I put a winding, a coil of wire into a magnetic field, we create voltage. And then when I alternate that magnetic field between a positive and a negative, which in magnet terms is a north and a south, I'm creating more and more power. The strength of the output depends on the strength of the input and the number of windings. So if I go back one slide again, if my input has, let's say there's 20 windings on my input. Okay, so if I have 20 windings here, and if I have 10 windings here, okay, I'm going to drop my power by about 50%. So if I'm putting 100 volts in here at the top, okay, I'm going to get 50 volts out here. Because once again, I'm creating magnetism here, but with 20 windings, but I'm only capturing half that magnetism with my 50 windings. Now again, I could do this or the other way around. If I'm putting 200 volts in here, okay, and this is only 50 windings, if I have 100 windings up here, I'm capturing more of that magnetism and I'm going to possibly put 400 volts out. Now the problem comes up is the current changes. So in this scenario, if I'm putting 10 amps in here, okay, if I'm putting 10 amps here of current into this side, and I'm pulling, and I'm increasing the voltage, I'm decreasing the current. So that's something to be really aware of, is whatever my current is on the primary side, depending on what's happening to voltage and the number of windings, it's going to change on the secondary side. Okay, this is very important to remember when we start talking about control systems, because that transformer has to be strong enough to drive whatever controls we're driving. So as I said, the input AC creates a varying magnetic field. Magnetic field induces a voltage onto the secondary windings. This is all dependent on the strength of the input and the number of windings. The voltage ratio, as I just explained to you, that's the difference in the voltages between primary and secondary, is equal to the number of turns, okay, or turns ratio, which is the primary to the secondary. The current ratio is exactly the opposite. If the voltage goes up, the current goes down. Now we have two types of transformers. We have a step-down transformer where the primary turns are greater than the secondary turns, which will decrease the voltage but increase the current. So if we have a transformer that has a 120 volt input and a 24 volt output, the ratio is actually 5 to 1, but the current is 1 to 5. In other words, if I have 5 amps, if I have 5 amps on the input side, okay, that's a 5A in my little mouse chicken scratch here, okay, and I'm going to increase this current, and I'm going to end up with roughly 25 amps, but at 24 volts. Now, this is not a realistic scenario. We often go from 120 to 24, but our current is much lower than that a lot of times. So again, whatever happens to the voltage in a transformer, the exact opposite happens to the current. And that's a very important point to remember. I'm going to ask you about that in the future. Again, what happens to the voltage, the opposite happens to the current or the amperage. A step-up transformer is where the primary turns are less than the secondary turns. Okay, in other words, we increase the voltage and decrease the amperage. So a VA rating is another term you need to know, the VA rating. It's the secondary voltage times the secondary amperage. Okay, if the secondary current draws more than the VA rating, the transformer is going to melt down. Okay, now what else is a definition of voltage and amperage? If we multiply voltage and amperage, what's that giving us other than VA rating? Power. It's the watts. So if I take voltage and amperage, okay, and multiply it out, I get watts. Well, VA rating is just another name for watts, but it's very specific to transformers. Okay, so if you go into a supply shop and have to buy a transformer, you have to know the primary voltage, you have to know the secondary voltage, and you have to know the VA rating of the transformer you need. And they look a lot the same, so you really have to look at the boxes. And just as a hint, always open the box and look at the actual transformer, because sometimes people return wrong things in wrong boxes. So you always want to look. Okay, control voltage in AC and HVAC overall is usually 24 volts is the rating. Now, when you go into shop, you're rarely going to get a reading of 24 volts. If I tell you to put a meter on a transformer in the shop, like on a basic electrical board or something like that, you're not going to get 24 volts. You're very likely going to get 26 volts. Okay, and that's because because the transformer's not under load. When the transformer's under load, in other words, everything's connected to it, that voltage is going to drop a little bit, but we still need it to be over 24 volts. So a transformer just by itself, you're probably going to get about 26 volts. If you ever get plain 24 volts out of a transformer that doesn't have anything connected to it, you're going to have a problem with that transformer. Okay, so sooner or later, that transformer's on its way out and you're going to have to replace it. This is just a basic picture of a transformer. Okay, this plate back here, the plate on the back of it is designed to be put on a square junction box, because National Electrical Code says that any junctions we make with line voltage have to be enclosed in a junction box or a piece of equipment. Okay, so this is designed to be mounted on a junction box. My low voltage side, or my secondary side, comes right out of the screws here. Okay, one is labeled R and one is labeled C. Okay, R is where I take is basically my line on the low voltage side. C stands for common. That's basically the equivalent of my neutral. If whatever voltage I put into this transformer, it should be dropping it down to between 24 and 26 volts. How to check a transformer? Okay, first of all, we take amperage readings. You take your VA rating. You have to know that. In other words, you have to know what your VA rating is. You ohm out the reading on the secondary side. You ohm the reading on the primary side. And then you go from R on the secondary side to L on the primary side. And I'll show you this when I do a diagram. Then you check from any wire to ground. Okay, why are we doing this? If I take a resistance reading across both terminals on the secondary side, okay, we're going to check and make sure that winding is good. What should I get if I take a resistance reading on the secondary side? What should I get?
24 volts.
No, resistance, not voltage. So my transformer's unplugged, disconnected from everything. I'm going across the 2 pins on the secondary side. What should I get?
Some number.
Some number. Because all it is a coil of wire. Okay? Some number. Okay? What about the resistance reading on the primary side? The PS, the primary side. So that's my load side. What should I get? It's a coil of wire.
It should have some number, but it's not if the load's bad.
Yeah, but in a good transformer, again, so good transformer, it helps to know what we're supposed to get. You're right, some number. If I take 1 meter lead and put it on the primary winding, and 1 meter lead and put it on the secondary winding, what should I get?
0.
Not exactly. If I get 0, I have a problem. What should I get?
OL.
OL. Because I shouldn't have any continuity between the primary and the secondary sides. Okay, remember, they're electrically non-connected. The only connection between the two is magnetism. Okay? If I take any wire or terminal to ground, to the case of the transformer, I should not get any readings. If anything is different from what I just went over, okay, in other words, secondary side, some number, primary side, some number, no continuity or OL between primary and secondary, or OL from any wire or terminal to the ground, we have a problem with the transformer. Okay, so OL or just continuity on the secondary side is a problem. Okay, if I don't get some number. If I get OL or 0, it's a problem. OL or 0 on the primary side is a problem. If I get any numbers between primary and secondary, we have a problem. If I get any continuity from the primary side or secondary side to ground, we have a problem. When I connect it, if I have voltage on the primary side, but no voltage on the secondary side, there's a problem. Those are the only 5 things that can go wrong with a transformer. That's it. Now, we also have a thing called multi-tap transformers. You're going to see these on the trainer boards that are on the walls when you get into the shop, okay? We have multi-tap transformers. Secondary side is always 2 wires. It's usually a blue and a yellow wire that comes out of the transformer that's on the secondary side. The primary side can be either 120 volt, 208 volt, 230, or 277, and it goes up from there. You can get them up to 460, 480, 720. But these are your primary ones you'll see, okay? They have 1 wire for each of these. Every wire is a different color, and someplace on the transformer, there's a label that says what color wire you use for each one of these. And then there's another wire called common. Okay, so you connect the common wire to one side of the primary circuit, to one side of the supply. You connect your either the 120, 208, or whatever to the other side, and you have to wire nut the extra wires off because they actually do have an electrical charge. Now, having said that, if I'm wire nutting these off, do I wire nut them individually or all together?
Individually? Individually?
Individually. If I wire nut them all together, I'm going to burn out the transformer. Okay, seriously, there will be smoke and possibly fire. Okay, so every one of them must be capped individually. Okay? A guy who taught me electrical way back when told me all electrical components work on smoke. If you let the smoke out of them, they don't work no more. And there's a little bit of truth to that. So wire nut them off individually, not as a bunch of wires. And this is just an example of a multi-tap transformer. I have my two secondary wires coming out of here. Unfortunately, these are the same color, but it's AC circuits. Does it really matter? No. Okay, one of these wires on the other side, probably the white, is going to be common. One is going to be for the 120 volt, one is going to be for the 240, and one will be for the 208. And they're all different colors. This just happens to be a black and white picture. Okay, and you look at the label on the transformer, and it will tell you what wire connects for what voltage. And you've got to be really careful about this. Because if you connect a 120 volt situation into a 240 volt circuit, it may not burn out the transformer. Okay, the transformer may actually stay running. But instead of having an output of 24 volts, you could have an output of 48 volts. Okay, so if you connect the wrong terminal, the transformer may not blow up, but you may melt down whatever you have connected to it. And I can tell you right now, Nest thermostats don't handle that too well. They like their 24 volts. They don't want 48 volts. Okay. Someone asked in the chat, and it's a worthwhile question, what does OL stand for? It could be open line or it could be infinite. Stands for the same thing, basically no path for the current to flow. Okay, so OL is either, it could be referred to as open line, you see that a lot, could be referred to as open load, but the big thing is that it's infinite resistance, no path for the current to flow. So again, every one of the answers that was other people put in there was correct. Just it's infinite resistance, no path for the current to flow. Okay, this is an example of a transformer in a circuit. Okay, we have our transformer in the center here. We know what the voltage is because someone labeled the primary voltage. And because it's an air conditioning circuit with a thermostat and everything else like that, I could say that it's a 24 volt down here. Now, on your schematics, I really want you to label the voltages, okay? Just again, because that's what one of our standards is, so you'll want to label 24 volts. Okay, this is a basic cooling circuit, okay? Anyone want to maybe tell me what it does? Anybody want to take a guess? Anyone want to take a guess about what this circuit does? Want to give me a sequence of operation? Okay, it does control the thermostat. Someone put that in there. What about if I said the 24 volt transformer provides power to a cooling thermostat? When the room heats up, the thermostat closes and energizes the component labeled C. The component labeled C closes, okay, another component. Okay, we'll talk about this. This is a relay coil, not how I like to see them drawn, but more importantly, energizes the G terminal, which closes or energizes the IFR, which closes the IFR contact and turns on the indoor fan motor on high speed. So again, the 24-volt thermostat energizes or provides power to the R terminal on the thermostat when the cooling thermostat, and I'm going to have to mute somebody here, when the cooling thermostat closes as the room temperature increases, it provides power to both the Y terminal and the G terminal, provides power to the IFR relay, which closes the contact, and we're going to talk about relays in a minute, and provides power to the indoor fan motor on high. Does everybody see that? That is a basic sequence of operation.
I just got a question. How you got number 24 from the bottom?
Because we know this is a cooling circuit, and all of our transformers in HVAC put out 24 volts on the secondary side.
Okay.
Okay. And exactly the reason you asked that is why I want, when you guys draw schematics that includes transformers, please put a voltage in there. Okay, write a voltage there. But
Okay.
it's 24 volts. Any other questions on this diagram? Because I'm going to skip to the next one in a second.
Can you try to explain it one more time, please?
Okay, let me erase some of my scribble here. Okay, so my 24-volt thermostat provides power to the R terminal. When the cooling thermostat closes because the room temperature goes up, it provides power to the G terminal and the Y terminal. The Y terminal provides power to my cooling relay coil. We're going to talk about this in a minute. But more importantly, on this schematic, it provides power to IFR. Okay, IFR, if you look at the legend, says it's the indoor fan relay. When this coil is powered, it closes the normally open contact of IFR and provides power to my indoor fan motor. Does that explain it for you?
Yes, thank you.
Okay. Now, when we start getting a little bit more complicated on circuits, we start getting into this situation. Okay, and understand when I've made notes on some of your schematics you've handed in about providing labels, this is why. Okay, so again, we provide power to a transformer, which as far as I'm concerned is incorrectly drawn because they forgot to put the two little things in there. Leave it to my textbook publishers. Okay, so we're providing power to the transformer because this side is my primary, which is the load on, and by the way, L1 and L2, what voltages are we talking about the minute we go to L1 and L2? Are we still talking about 120 volts?
240,
Say that again?
240, 220.
Yeah, we're in the 240, 208. Okay, we're no longer in 120 volts because I now have two lines. Okay, I no longer have a neutral here.
We've
Now
actually had a lot of schematics come up through this course where L1 and L2 was meant to depict 120 volts and not 240 like you would think.
Yeah, and it's really weird. It all depends on how the publishers are drawing them, but in air conditioning, okay, we need to realize anytime we have that compressor, okay?
One of the pet peeves of mine when they put L2 and then you look at the equipment and you're like, wait, this is not...
Oh, I 100% agree with your pet peeve, okay? Yeah. But let's in this case, let's go with the 240.
Definitely is.
Okay. And I wish they would label it too. The textbook authors drive me nuts on this. Okay. But here we have two switching devices. Now, from a personal safety standpoint, what can you tell me about L1 and L2 in terms of safety? Do I need to turn both circuits off in order for the equipment to be safe?
Yes.
Yes.
Yeah, I have two hot legs here. I no longer have a neutral. Even though I never trust neutral, I don't have a neutral. Okay, so this transformer down here is 240 to my standard of 24. Okay? So again, sequence of operation. I'm providing power to my transformer. The transformer secondary is providing power to the R terminal of the thermostat. Okay, this system switch, you see quite a lot. Okay, the system switch is basically the on or off, or heat or cool or off setting on your thermostats. So if the system switch is in cool mode, that's closed. The room temperature goes up and provides power to two terminals on my thermostat, the G and the Y. The Y terminal provides power to my contactor, because again I have a legend up here. Okay, the contactor coil magnetically closes C and C. At the same time, the G terminal provides power to the IFR relay. Okay, and IFR closes and energizes the indoor fan motor. This is another one of my pet peeves, and by the way, you guys will see this on equipment in the field. For some reason, certain parts of the equipment, they don't shut off L2. So even if the equipment is shut down from the thermostat, you might still have power on components. So before ever you reach in there and touch something, make sure it doesn't have power with your meter. Okay, because notice IFM, which is the indoor fan motor, doesn't have another contactor on the L2 side. So even if IFR is open, this motor still has a power on it. Okay, and this happens quite a lot in the field because it's cheaper to put in a single pole relay or a single pole contactor and not do a double pole. So again, just be very careful when reaching into equipment. But again, the sequence of operation: transformer provides power to the R, system switch is on cool, system switch is closed. When the room temperature warms up above the set point of the thermostat, we provide power, 24 volts, to the G and the Y terminal. It energizes the contactor coil and the indoor fan coil. The indoor fan coil closes the IFR contact, and the C coil, the contactor coil, closes C and C. When those close, it energizes the compressor and the condenser fan motor. What's this component right here? Anybody?
The compressor
running.
It's a capacitor. Okay, in this case, it's a run cap. We're going to talk more about those when we talk about motors, but I just want you to know what that is. It's a capacitor. Okay, it helps us make our motors run more efficiently and provide the power we need on them, the actual force. Any questions on what I went over on this diagram? There's a lot more here than what I went over, but that's for a reason. Questions? Okay, so again, the ratio of the windings is pretty important. Okay, so if I have 1,000 turns of wire on a 120 volt circuit, okay, secondary side has 500 turns of wire, we're cutting the voltage in half. What are we doing to the amperage?
Doubling it.
Yeah, we're doubling it. By the way, look at how the voltmeter is connected. Is that in series or parallel with the load? The voltmeter's over here. Yeah.
Parallel.
Oh, parallel. Okay, I know a couple people on labs submitted on the questions got that incorrect, and I think I made a bunch of notes on it. But the voltmeter's connected in parallel with your loads. Okay, because it's next to. Load is still getting power. Your meter's getting power, same power the load is getting, so it's connected in parallel. Any questions on transformers? Okay, let's talk about, I want to talk about relays, okay, and contactors. So we're going to switch over because, again, it's part of the same conversation. Okay, so if I have a transformer in a circuit, and again, I'm going to just go to my cheat sheet on my transformer. By the way, start making a diagram cheat sheet if you're using PDF Expert, and you can just drag and drop things over from a sheet you have with all the symbols on it. Draw the symbols out, and if you're using PDF Expert, okay. Hey, someone put a note in here. You guys can't hear anything. Can you guys still hear me?
Yes.
Okay.
Yeah.
Okay.
Yeah.
I can.
Okay, thank you.
I can hear you.
Okay. So if I have a diagram where I have my transformer in here, okay, and I have some load up here. I don't care what the load up here is. I have some load up here. Okay, might be a light bulb, might be a motor, might be something else. Okay, so I have this load up here, but I want to turn it all on and off with my cooling thermostat down in the space. Okay, in other words, I have a cooling thermostat, and I want to turn everything on and off with my cooling thermostat that's on a wall someplace, okay? So this is on a wall in some kid's room. I don't necessarily want my 240 volts on the wall. Okay, it's dangerous. That's why I use 24 volts. Okay, so what do I use to control this line voltage load, this heavy load, with my thermostat that's down in the space? Okay, because I don't have 120 volts, 240 volts coming through here. I have small voltage coming through here. Okay, what can I use? Some of you guys have had this before.
A relay?
So what was that?
A relay?
Yeah, we want to be able to use a relay and a coil. Okay, so I'm gonna use a normally open contact up here. Okay, put a normally open contact someplace in here. Okay, but down here, I also have to have the other part of it because the two of them always go together. You have to have a coil because there has to be something to magnetically close this contact. Okay, so down in the bottom part of it, I know I have one around someplace. There it is. Okay, you have to have a coil. Because the two of them have to work together. Okay, so to complete the circuit, okay, all I'm doing is putting in because I have to have a complete path for the circuit. Now, what's missing? And again, I'm going to talk about relays and contactors in a second, but what's missing from this schematic?
A close for the contact.
A what?
Labels.
Labels is what I was looking for. But what was the other thing somebody said?
A close for the contact at the top.
You mean the slash across it?
Yes.
Okay, when we draw schematics, we want to draw in my normal position, which means what is it when it's unpowered? Okay, so if I want this to close when we energize, my schematic's going to be drawn in the normally open position because this isn't energized right now. Does that make sense?
Yes, thank you.
Okay, so once again, got to get labels on here, okay? And we have voltage labeled here, so I'm not going to worry about that really. And I'm just going to do, just because I didn't put another contact over there, I'm going to say L1 in neutral. Okay, so that's a basic schematic using a relay to turn on a line voltage load. So our whole purpose of contactors and relays is to allow us to use a low voltage circuit to turn on a line voltage or a high amperage load. It's a safety thing. It's also much easier to run smaller wire because I can run 18 gauge wire, 22 gauge wire on the low voltage side. Okay, and the relay and the contactor, this whole idea of a coil and a contact handling different voltages, okay, is where we come down to the whole premise of, it's the building block of the building control systems, okay, computerized building controls, direct digital controls. Everything you do works on relays and contactors, okay? So we've talked about transformers so far. That allows us to have our control circuit. Now let's talk about what allows our control circuit to energize and de-energize loads on the line voltage side. And that all comes down to relays and contactors. So the relay is an electrical device that consists of a coil and a set of contacts. The coil and contacts are isolated from each other. There's no electrical connectivity between the coil and the contacts. It's designed to be usable where one circuit must control another. Okay? It's designed to be usable where one circuit must control another. We have several schematic symbols, and you just saw me use two of them. We have a relay coil. By the way, sometimes you'll see this drawn differently, okay? Different people, different publishers draw these coils in different ways. Okay, so you'll see some people are going to draw these coils just as a coil. That's a coil of wire. Sometimes you see it drawn as a circle. Please do not just draw them on your schematics as a circle. They look too much like light bulbs. Please use the relay coil symbol that I'm showing you here, sort of like the two triangles together. It's very clear it's a relay coil, okay? And it doesn't get mistaken for a single pole, for a shaded pole motor or anything like that. It's a very clear coil. Okay, so please draw your schematic symbols that way. We have a normally open contact. Bottom line is, when the relay coil gets energized, a normally open contact closes. We have a normally closed contact. So when the relay coil is not energized, we have a path for power. When I energize the relay coil, that opens. Okay? So these are my three symbols for a relay and also a contactor. We have a relay coil and a contactor coil, always. We have a normally open contact and we have a normally closed contact. Both of these do not always have to be on the device. Different devices have different sets of contacts, but it's either normally open, normally closed, or sometimes they have both on the relays. So the relay coil is a spool of wire wrapped around an iron core. Why do I care about that it's wrapped around an iron core? What's so special about that iron core?
It's highly conductive and magnetic.
It helps create that magnetism. Okay, I spin a iron core that's slightly magnetized inside a spool of wire, or I energize a coil of wire around an iron core or any piece of metal, quite honestly. Okay, a magnetic field is going to be generated. That magnetic field is strengthened and directed by that iron core. When this field is generated, it pulls in what we call an armature. In other words, a moving part that opens or closes a set of contacts. When a relay is shown in a schematic, it is always shown in the de-energized mode. A relay is always shown in a de-energized mode. Every coil has a voltage rating. When you look at the side of a relay, you always see a label or a contactor. The rating is the voltage that you may apply to the coil. Don't put the wrong voltages on the coil. The voltage rating is the rating that you can apply. These ratings are normally 24 volts, but as soon as you start talking about refrigeration and some of the other parts of the trades, the coil can be 120 volts or 208, 230. Be careful. Always check the coil voltage. Even if you think you have a 24 volt coil, look. The coil won't work if the wrong voltage is applied. If you put 120 volts on a 24 volt coil, it's going to melt down. If you put 24 volts on a 120 volt coil, nothing bad is going to happen. It just won't work. The coil rating, again, is stamped on the side of the relay. The coil is a load in the schematic circuit. So if you look back at my other schematic, this coil over here, okay, the coil is a load. Oops. It's something that does work. It uses power. Anytime you have a coil in a circuit, it has to go back to the transformer. It has to go back to the other side of the source. It is a load. Don't put two coils in series. They don't work too well. Relay contacts are the switching device of the relay. Normally, when I say normally open or normally closed, it refers to the position of the contacts when the coil is de-energized. Relay contacts come in two varieties. They're either normally open or normally closed. That's our two choices. There's no halfway in between. It's either open or closed. Relay contacts are attached to the armature that is moved by the magnetic force of the coil. The contacts have metal points that come in contact with each other. These points complete the circuit. This is instantaneous. You put power on a relay, within a split second, those contacts close. There's no bouncing around. There's no sparking around that goes on if it's working properly. It is an instantaneous close. The contacts are labeled in the schematic to correspond to the coil that controls them. For example, the coil might be labeled IFR. Once you have the coil labeled, you'll label the contacts including the coil label. In other words, so when I look at a schematic, I know that the coil IFR is controlling any contacts that are labeled IFR with a number. Does that make sense to everybody? Okay, coil is labeled with a letter designation. The contacts have to be labeled with the same letter designation, and then you can add a number on it to like 1, 2, 3. Okay, this is why labeling starts becoming so important. Normally open schematics are shown on a schematic as an open set of contacts. When the relay coil is energized, the contacts close, allowing electricity to flow through them. Normally closed contacts are shown on the schematic diagram as a closed set of contacts. When the relay coil is energized, the contacts open and don't allow electricity to go through them. Again, normally open, normally closed, shown in the de-energized position. The contacts are always rated with the number of amps they can control. Okay, they're also rated with the type of load they control. It can be inductive, like a motor, or resistive, like a heater. We talked about the difference in the circuits because of resistance and amperages with motors and heaters. Okay, motors, anything with a coil, like a motor, creates its own resistance and the amperage changes. Resistive loads, like any type of heaters, heat strips or whatever, okay, their amperage doesn't change. It's stable. Okay, but it's very important on the contacts. You can't put a contact rated at 5 amps on a compressor that you know under running conditions will pull 60 amps. You can't do that. It's going to melt the contacts down. Now, here's the important part. With inductive loads, the amperage spikes when it's starting. Okay? Let me see if I can explain that a little bit. When I first turn on a motor or energize a coil, for a split second in there, there's no resistance. If there's no resistance, the amperage goes way up. As soon as the coil starts generating its own resistance, the amperage will come down and will level off to the running amps. Okay, now, this spike up here, any device that's controlling the motor has to be able to handle this spike. Once we're back down to our running amperage, there's really no issue. Now, some of you guys, I did go over this a little bit when I spent a week with you guys last term in York, so I think I touched on this, or I mentioned it to you. Does anybody remember what I said about the level, how high this amperage can go over my running amps? Does anybody remember? This was LRA.
About 6 times.
Yeah, about 6 times. So this is labeled either FLA or RLA. Okay, this is labeled either FLA or RLA, and that's for full load amps or run load amps. Okay, LRA is locked rotor amps. Okay, locked rotor amps only happens when the amperage spikes at startup and the motor or whatever isn't turning yet. The amperage is way up there. It's about 6 times higher than my FLA, which is full load amps, or my RLA, which is run load amps. Okay, there's about a 6 times difference. With resistive loads, the amperage remains constant. Make sure the contact ratings, okay, exceed the maximum amperage that the load is rated for. The contact has to be able to handle that power. Okay, run load amps I just went over. Locked rotor amps I just went over. I use the magic number 6 because it's in the middle of the book number 5 to 7. Okay, 6 works pretty well for just about everything I've seen. LRA and RLA must be considered when choosing a control device. Gotta consider it. Okay. Relays. It's very important to remember that the coil and the contacts are isolated. Okay, again, if we go back over to my drawing here, there's no electrical connection between the coil and the contact. Okay, there's no electrical connection between the coil and the contact. They're completely isolated. And we got to remember that because we're using different voltages on the two. A technician can de-energize and remove the wires from the relay contacts for the purpose of ohming it out, even if the coil is energized. In other words, I can safely disconnect the relay contacts. In other words, I can come in here and I can remove this wire there. I can remove this wire there. I can connect my ohm meter here and here. I can re-energize the circuit. Of course, when I mess around with wires, I've turned the circuit off. But once I've isolated that component, I can re-energize the circuit, and I can see what happens to this contactor by opening or closing it based on the thermostat. Okay, so again, they're electrically isolated. Okay. It's a good way to determine whether or not a relay is working properly. There's better ways, but it's a good way to determine. So if a coil is energized with 24 volts and the technician isolates the contacts and reads 0 ohms across the normally closed contacts and infinite ohms across the normally open contacts, we know the contacts are not switching positions. It's either the coil is stuck or is broken, or the contacts are stuck. Okay? I don't like playing around inside circuits, so I don't like using an ohm meter anywhere near a powered circuit. So another way to do this whole thing is to do it safely with your voltmeter. If I have my voltmeter here and here, and let's say this is 120 volts, not the 240. Okay, it's the 120 volts. Okay, I close this thermostat. In other words, I adjust the set point on a thermostat to make it close. I energize this relay coil in the process, and if I have 120 volts here, what's my problem? Thermostat's closed, coil's energized, I have 120 volts between that point. What's my problem?
The coil's down.
Something's failed because it's not closing the contact. That relay has to be replaced. You're not going to fix these. Okay? And that's how you really want to troubleshoot these. Disconnecting it, ohming it out doesn't make a lot of sense. Okay, if I have power on the coil, okay, and I know I have power on the coil because I've measured it, and if the relay doesn't close, if the contact doesn't close, hey, we have a bad relay. You're going to pull it out and replace it. That's about all you can do. Okay? So, again, example 1, I have a switch 1, a coil 1, and C1 normally closed, C1 normally open. Okay? In this case here, my normally closed ball is energized. Okay? If you look closely, you can see it's a little bit energized. I used to have these blue and red. I don't know why someone changed them, but okay, this one's de-energized. This is open. This is closed. Normal position. Coil is not energized. I energize the coil. Okay, this swaps. My normally open closes, which is right there. My normally open, or my normally closed, opens. So again, I've energized the coil. These have swapped positions, if you look. Swap positions. That's how normally open and normally closed works. We always draw our schematics in the de-energized position. Okay, this is your most commonly found relay. Okay, it's known as the Mars relay because the Mars company, which is an electrical manufacturer, made this relay. Okay, it consists of a coil and 2 sets of isolated contacts. Each set of contacts has a normally open and a normally closed contact. Okay, so if we look at this with it labeled, my coil contacts are right there. Then I would provide power, line, even though it's common, it's just common with respect to the two switching devices. I could provide two sets of power. It could be different voltages. Everything is isolated. So on pin 1, which is right here, I could have 24 volts. On pin 4, which is right there, I could have 120 volts. Or I could have two completely different 120 volt circuits or two 40 volt circuits. Okay? Then I have a normally closed pin right there and right there. And I have a normally open pin right there and right there. This group of pins all works together. This group of pins all works together. So when I'm designing a circuit, in other words, a control circuit that I wanted to do a specific thing, I can use a single relay as long as the operations can all be controlled with either power or no power on this coil. When it's drawn out in a schematic, it looks like this. 1 and 4. It's two completely different circuits. There's no electrical connectivity between this side and this side. There's also no electrical connectivity between the coil and the rest of the relays. It's all independent. This coil gets powered. Let's just say gets 24 volts. Coil gets 24 volts. This closes. That opens. That closes. That opens. So whatever energy is being put in here will now come out of 3 and nothing out of 2. Whatever power is being put in on 4 will come out of 6 and nothing out of 5. When I turn this off, it goes back to its normal position, and 2 and 5 would be energized. So we have 3 sets of pins for each circuit. I have 1, 2, and 3, 4, 5, and 6, and then I'll have a set of pins on the side of the relay someplace that is for the coil. Any questions on the Mars relay? This is sort of important. Okay. Contactors are the same thing, basically. They're the same as the switching relays. They work in the identical way, except they're larger in size and can handle more amperage. The contacts, unlike in the relay, the contacts in the contactors are visible. And the larger ones, we can actually change the points and the springs out in. They're usually a definite purpose. In other words, they basically have normally open. They're used to energize our larger motors, which include our compressors. Contactor coils are rated by voltage. Contactor contacts are rated by amperage. Okay, they're normally written on one side of the contactor. Do not install a contactor that goes over either of the ratings. Contacts are very, very important. Okay, don't install anything that goes over the ratings. Okay, this is just an example of a contactor, some different configurations. All of these terminals are normally open. This one connects to this side. This one connects to that side. This one connects to that side. L1, L2, L3. Now this one is one you'll see very often in residential air conditioning. L1 and then L2 doesn't switch. Remember I showed you that I said that's a pet peeve of mine because it leaves L2 energized. It's a safety issue, but be aware it's cheaper than having a double pole contactor. So L2 may come in on this side, it's always energized. My coils connect here, and you can't see it, there's another connection on the other side. In this case, my coil connects here and here. Okay, looking closely at this contactor, what's the coil voltage?
120.
120. Okay, you can see it on that one. What's my amperage?
30.
That's my, 30. That's the amperage of the contacts. Okay, over here I can't quite see it, but they give you an LRA and an RLA number here based on your voltages across here. You've got to look at these labels. Very important. This one I can see the coil voltage barely. It's right there. It's 24 volts.
Yeah.
Okay? So again, be very careful to the voltages and amperages, okay? It's very important. Do not wire coils in series. I've seen somebody do that. Bad things happen. Okay? The contacts, okay, get connected to a coil, which is called a holding coil. Up top of there, I have my stationary contacts. Okay, then I have movable contacts that fall on top of that. Okay, I have my whole assembly, the plastic that goes around it to try to isolate it. I have my coil connections. Okay, and what happens when the thing closes, okay, we provide power. When this closes, we provide power to the devices. Okay, so again, when the coil is energized, when that becomes energized, my normally open contacts are going to close. They're going to close at the same time. This is very important when we're dealing with larger systems, especially three-phase. We have to have all of our contacts that you might see on the coil or on the contactor. Like I have 3 contacts here, 3 sets of contacts. These have to close at the same time. I can't just have L1 and L2 going to a motor. I have to have L3. It's very important it all closes together. Okay, a wired contactor, okay, and basically how you would see it in a schematic. Okay, contacts and my coil. Now, a couple things to note. When you're servicing equipment, when you're doing preventative maintenances, you want to always look at this area of the contactor. Okay, and I'll see if I could find you guys some pictures of some bad ones. I know I have some pictures of some bad ones. But you want to look at this area of the contactor. Whenever you open or close a high voltage switching device over time, these contacts have little points on them. Okay, they have little sort of brass points that pull them together. These points are going to wear down. They're going to start building up carbon. So contactors in an air conditioning system in your part of the country have probably a lifespan of 5 years. About at 5 years, you're going to start seeing some burn marks here. It's going to start looking like a lot of carbon buildup. Carbon is an insulator. Believe it or not, this $60 part, that's by the way the customer price, $60 part can actually take out a $500 compressor if these contacts start building up too much carbon. Because as the electrical flow is reduced to the whatever's connected to it, the amperage is going to start going up. Because all of a sudden I have resistance because of the carbon buildup in series with a motor or 2 motors. That's not a good thing because, again, now I have a series circuit, so I'm splitting voltage. This device will start eating voltage because of that carbon. It will start producing heat, and it will just get worse and worse as the time goes on. A schematic of a contactor is shown like this, okay? It's a coil that might be on the low voltage side and two sets of contact. When you draw your schematics, you'll label these, okay? And the labels have to match. Like if I have C or CC for compressor contactor or condenser contactor, the labels on the contacts have to match. Because that way I know that this coil is connecting these contacts. Oh, they do. We did find some pictures. Okay, this is what the contacts are going to start looking like after time. Okay, this is new. See how nice and shiny it is? This has been in there a few years. Same thing here. This is new. This has been in there a few years. We want to replace these before they get to this point. This is really bad. It's very badly pitted. Okay, so you want to replace these before they get to these points. Okay, anybody have any questions for me?
With these contacts, can you replace just that individual part inside of them, or do you have to replace the whole contact?
If I was using, I'm going to give you two answers on that. Okay, if I was using one of these heavy commercial ones, my purchase price was probably a couple $100, and if I could get a rebuild kit for it, I would replace the contacts. Okay? If I'm doing one of these over on the left-hand side, the residential, the cheap ones that I buy for maybe $6, okay, I'm not going to waste the time replacing contacts. I'm going to replace the whole contactor.
Yeah, that makes sense. Okay, thank you.
Okay, the big commercial ones that you see on three-phase equipment, chillers and stuff like that, and I'm going to show you some pictures of those when we get into chillers. But the big commercial ones, and I think there's some actually, yeah, most of your labs, most of the shops on the campuses have some. They actually have their specific rebuild kits where you just rebuild these automatically as part of a preventative maintenance visit. Any other questions on relays, contactors, or transformers? Okay, just as a reminder to everybody, you guys do have some homework assignments due on Monday. Please don't wait till the last minute. I don't do well with late work. Please make your discussion board posts, and when you're doing your discussion board posts, please answer my question. Saying here is nice, tells me you were here, but I do need you to answer my question, okay? I'm already going easy on discussion boards because I'm supposed to be having you guys do 2 responses to other people as well. But just answer my question. Let's just play by the rules on that one. And the last thing I have to say is you guys have a good weekend. Enjoy.
You too.
You too, sir.
You too. Goodbye.